Awesome. Welcome, everyone. This talk is about re-rankers and improving your RAG and agents using re-rankers and fine-tuning them. A quick introduction about me. I do machine learning at LanceDB. Previously, I co-authored Alternative YOLO framework, and before that, I did ML at Weights and Biases. If you have any questions about this talk, after this talk, you can reach out to me on Twitter or LinkedIn. The topics that I'm going to cover today are re-rankers, what are they and how they're different from embedding models, training and fine-tuning them, and then the trade-offs involved when you decide to use re-rankers in your pipeline. So first of all, where does re-ranking fit in? If you have not used re-rankers before, this is a general RAG pipeline. User sends a query, then you use that query and do a bunch of things there. Then you send that query to a retriever, get back some results that are then fed to a generator or LLM in this case. Re-ranker fits right between the second last and the last step, which is it gets the results of your retrieval process, and then it re-ranks them, rearranges them basically, keeping more relevant queries at the top. So how does this work? This is more of a visual representation of what's really happening when you re-rank. So, when you're searching an embedding space, and by the way, in this talk, we basically deal only with semantic search mostly. There are other types of retrievers that don't use semantic search, but this is mostly vector DB centric. So you search for a query, then you receive a bunch of results, as you can see in the second part of it. What a re-ranker does is it basically takes those end results and rearranges them, as you can see, and then finally an LLM completes those the query or answers that query or generates an answer based on the retrievers. So the difference between an embedding model and a re-ranker model is that an embedding model generates a representation of your data set in an embedding space, so that semantically similar documents or data points are kept close together. A re-ranking model, basically what it does is it takes a bunch of relevant documents and it rearranges them based on their relevance with respect to a particular query or a question. Right? That's the key difference. What does a re-ranker look like? So when we talk about continuing on the difference between embedding models and re-rankers, when we talk about embedding model, these are biencoders, right? Your inputs, for example, if you've embedded a document, you chunk it down into different chunks and you process them independently, right? There's no relationship between how you chunk document A, document B. So the model looks at it independently. The cross encoder, what it does is it takes two inputs, pairs of inputs together, and it creates a classification score, which is sort of a similarity score. And it sort of does a dense representation of both of them together so that they can interact with each other. Both the sentences or both the documents can interact with each other throughout the encoding process. This is why it can form better similarity matching, right? And this is why it's so powerful. Before we go on to the training process, I just wanted to clarify that if a question might arise that if cross encoders are so powerful or re-rankers are so powerful, why not just use them, just eliminate the embedding models? Problem is that these are also very costly. If you just use re-ranking across 5, 10, 15, 20 documents that you already retrieved that are already similar, it's going to be real time. But if you do it across millions of documents, it's just going to waste a lot of time. It's never going to be real time. So there's a good trade-off there. Awesome. And then the other thing why re-ranker is really powerful is that when you attach a re-ranker to your retrieval pipeline, you don't have to re-ingest your entire data back to the DB, which means that if you change the embedding model, that is another way to improve your re-ranker, another way to improve your RAG, you have to re-ingest your data. So re-rankers are also not disruptive to your pipeline. These are the two advantages. Okay, so in this study that I performed, here's what I did. And this is how you will train any re-ranker model out there. So you have a data set, and the data set is pretty much a context and a query and its context, and with a bunch of negative context and a real relevant context, which is a positive, right? So here I had um, Google QA dataset that is available on Hugging Face, and it had 2 million rows. What I did was I created a test set of 5,000, and then I used the other ones for validation. So basically, the process is you take the data set and you mine hard negatives, because you're training a re-ranking model. So it's really important to have the data set that's really difficult to beat, right? So you cannot have one relevant document and a bunch of non-relevant documents, because then it's too easy for a re-ranker model. So what you do is you mine for hard negatives. So what are hard negatives? Hard negatives are literally negatives or wrong answers that have closer semantic meaning to the, the context, right? And you can do that using an independent embedding model. By the way, all of this utility is available on Sentence Transformers latest release, so you can use that as well. And once we have that, you can choose any evaluator you like. You just run crossing entropy loss, and that's it, right? That training architecture is pretty much the same across all embedding re-ranking models. But last year, or in a couple of years, a new architecture called late interaction has gotten really popular. So let's cover that as well, because we'll also use that as one of the re-ranker models in this study. So you've seen cross-encoder models. What they do is they literally process inputs or the query and context in pairs, right? So the good part is that they are really powerful. The bad part is that you cannot just create embeddings and save them offline, right? You have to generate these ranks together in inference time. What Colbert architecture does is it can pretty much process both query and context separately, which means that it extracts token level embeddings from your context and saves them offline, right, in a vector database or whatever toolkit you like. And finally, once you receive the document, right, they resume from that part where they calculate the token level embeddings from the query, and then finally you can extract that you already did for the context pairs, and then you can run maximum operation and calculate the token level embeddings for the entire document. So it pretty much does something that cross-encoder does, but it provides you with an option of late interaction, which means that you can do a part of the processing beforehand and keep it offline. So this kind of architectures are getting really popular because they combine the best of both worlds. They're really powerful, but they're not that slow at large scale. So benchmarking with LanceDB is super simple, and that's what I did for this study, and we'll see the results now. To use any re-ranker model, you simply can import them. We support almost all of the popular re-rankers, and you simply attach that as a part of your search pipeline, saying something like re-rank and pass in your re-ranker. Here, this is an example of using Colbert re-ranker. I have not covered Colbert and other API-based non-open source versions of re-ranker models because you cannot fine-tune them yet. Okay, now I quickly run through the experiment setup because I just have, I'll quickly finish this up and take questions if there are any. So the data set, as I've already told, is GoAQ data set, 3 million query and answer pairs. First 2 millions I've used for training. The next 100,000 are ingested in LanceDB, and from that, we will take 2,000 samples and try to calculate the hit rate. So it's a decent problem. It's not a toy problem. It's not a scale of toy problem. Searching across, searching 2,000 documents across 100,000 documents is pretty decent scale to test out. The base models that we use for re-rankers is one very small model that is a toy model, and then Modern Bird base. Modern Bird is an innovation on the original Bird base by Answer.ai and Lighton, and it's a relatively larger model, right? Okay. Baselines, these models are irrelevant because the baselines basically concern the baseline of the embedding model. The embedding model that I used is mini-LM, but we won't touch it, so it's irrelevant. We'll just care about the hit rate of top 10, which is what is the accuracy of getting the right document if we extract 10 documents at a time from a vector search result, and then top five. So these are the accuracies. And baseline model re-ranking performance. So what we've done is we have just taken these base encoder models. These are not trained for re-ranking yet. So you can see the results are very bad. It's like worse than random. So both of them give us 9%, 4%, 9%, 4%. Right? Now let's look at the trained result. So we trained the base models, and this is the naming convention. We have re-ranker architecture that we use for the re-ranker head in a way. You can attach classification head to an LLM, things like that. So just the architecture head that we use, the base architecture, the number of negatives, the hard negatives that we extracted, and number of epochs it was trained for. And so we use Colbert head on top of modern BERT, and we use Colbert cross encoders on top of modern BERT, and then cross encoder on top of mini LM, and the same for mini LM as well. So this is more like an ablation study. You don't have to really remember these numbers, but what I want to show is a general trend that re-rank at 5 went from, as I said, 48 or 48 point something to the best at 60. And the same thing happened with full text search. Obviously, it also improved, but it's not the focus of this talk. And then hybrid is a combination of both. It also went up. So these are all top 5. In top 10, which is like extracting 10 documents at once, it also went up from 60 to 67 or 68, and similar for FTS and hybrid search. Okay, key findings, right? So vector search performance improved significantly. As I said, showing up to 12% improvement in top 5, about 7%, 6.6%. Full text search also improved. Obviously, it showed more improvement because of different reasons, but essentially full text search is a different algorithm. It's not using semantic search. So the improvement can obviously differ a lot from the semantic search based operation, but this is not the topic of this discussion, so I'll just move past it. Architecture comparison, yeah. So modern BERT demonstrated the strongest performance, and this is also like expected because it's a large model. MiniLM is a toy model, but the takeaway here is why I chose 2 models here is that even across a toy model, it improved significantly. So it shows that this method itself is pretty decent if you're trying to just improve your RAG or agentic setup without too much disruption. Okay, but that's not it. I mean, no one trains model from scratch these days. You can also just fine tune your existing re-rankers, and the setup is pretty much the same. The same pipeline will work. So I tried that again. So Answer AI released their dedicated re-ranker model called Colbert Small, and other versions of it. I just chose this, and then I ran control tests, which is like the baseline test, and we got 59 and 68 vector hit rates at top 5 and top K respectively. And on fine tuning, it improved significantly again. So even using a dedicated re-ranker, you can further improve it by fine tuning, right? So you can see about 2% increase in top 10 and around 3% increase in top 5 vector search results. Now, the question here is, the takeaways are, should you train a re-ranker model from scratch or fine-tune? All things considered, my advice is go for fine-tuning first if you're unsure, right? Otherwise, just you can follow this guide. So if there are no re-rankers available for the base model of your choice, you obviously have to train. It depends on the base model that you want to use. Although I'm not sure why you would like to use something that does not have a dedicated re-ranker, but there can be moments like that. And your data set might have become specialized enough. So for example, you started with a general data set, and then now it's specialized in a particular field like medical, legal, whatever. And the distribution has completely drifted apart from the original distribution. So then it should obviously tune to align your model to the data set that you're working with. Things to be careful about is that fine-tuning an existing architecture is much faster. It applies across the board to every architecture. And another thing to consider is that if you fine-tune a model for a really long time, right, on a bad data set, it will get worse than even baseline instead of improving. So that's something to be careful about. The trade-offs. So trade-offs, obviously, no free lunch. We add something to the pipeline, we will have some latency. So here I've chosen L4 GPU, which is comparable to a T4 GPU because it's the cheapest, most readily available on all collabs. Obviously, you can use much faster GPUs and you will see much lower latencies. But just to study the latency here, top 10, we see around 30 milliseconds in the case of modern BERT. Uh, but the best performing model, which we have, Colbert Answer V1, that does not show like more than 10 millisecond latency from baseline. So it's like not very costly if you're running on even a cheap GPU. And the bottom chart shows at various top Ks, not just at 10, but even at 50, at 100. So really large top Ks, and you see the slowdown factor is of the best performing model is just 1.35. It's not that big of a deal to add few tens of milliseconds, right? Now, finally, you can also just stick to CPUs instead of GPUs without any acceleration. Even then, they just had a few 100 milliseconds. Now, if this number is too large for you, you can go for a GPU. But in most cases, few 100 millisecond of latency does not really make it or break it. So you can make that informed decision of trade-offs by yourself. So finally, I just like to finish with this. Who should not use re-rankers? Right? The trade-off is that they add some latency. If you're really tight on latency, even increasing it by 10 milliseconds is bad for your use case. You should not think of using re-rankers. You should stick to other ways of improving your RAG, which is embedding models, etc., which we've not covered here. But other general cases where adding up to 50 milliseconds, 100 millisecond latency is not too much, you should definitely exploit re-rankers, because the good thing about re-rankers is that you just need to plug it in. If you don't like it, you can just take it outside. Just plug it off. It does not matter, right? Unlike embedding models. Okay. Bonus, I have not covered fine-tuning embedding models, but you can do both of these things together. You don't have to stick to one. So we covered re-ranking here and fine-tuning re-rankers, but there's another study that I did where I tuned embedding models. So combining them together takes us further. So we got around with the best tuned embedding model, we improved the baseline from 48 to 62 and 60 to 69. But then even then, re-ranking helps. It further improved from 62 to 64 and 69 to 71. So you can even do that as well. That is in further reading. I have not covered that in this talk. Awesome. Thank you. I will drop the link to this report that deals with the re-ranking aspect in detail, and I'll also, and this also part 2 of this particular block covers the embedding models as well. So I'll finish it here and try to answer questions that you might have. Question from Peter: how do you decide when re-ranking is sufficient versus full fine-tuning is necessary to improve RAG performance? Well, by full fine-tuning, I think you mean fine-tuning both embedding models and the re-rankers. I would say the re-ranking aspect is so cheap that you can just plug it in, run a small evaluation, and then you'll know for yourself. It does not take a lot of time. That's the best part about it. So just try it out. A question from Anonymous: are there best practices for optimizing latency when introducing re-ranking in real-time pipelines? Yes, best practices are that you preload and pre-warn the model in a container or on a GPU. So the latency is almost negligible for 5 to 20 like pairs of a document query. Don't just load it for every query. And yeah, that's pretty much it. You can choose small models. Small re-ranker models perform really well. You don't have to use really large billion parameter model. Could you walk us through how you format data for cross-encoder fine-tuning? For example, you mentioned, yes, that is pretty much cross the formatting. You don't require a lot of formatting. The standard context and query pairs is enough. You basically combine the right context with a lot of negative context. But the article that I shared covers that in detail and also provides reproducible code, so you should check that out. Um, okay, for tasks with highly specialized language, you mentioned fine tuning necessary. What are some effective strategies for constructing high quality training data set for re-ranking specialized? So what you can do is, if you think that your just the documents that you have are really high quality, the proprietary documents that you have, you break them down into context chunks and then ask an LLM to generate synthetic questions from it, like 5, 10 questions, and then you have it, your query context pairs. That's the easiest way to go about it. But having a human in the loop for evaluating that is good, because LLMs hallucinate. So you have to be careful about that. Okay, I think that is it. Those are all the questions. Okay, I will finish this up now. Thanks for joining. Have a great day.